this session, I'll be going over how to actually run an RMG job, and then what all the different parts of the input file mean. Right, so starting off with the sort of general procedure for running RMG or any other Python script from the command line. So in general, this is going to be like the structure of your command. So you start off with Python, which is the program we're running, and then you need to provide the path to the main RMG Py script. And then you can provide any options, and then the path to your input file. And so in general, for users of the command line, this can be a bit confusing, but sort of the key is always knowing and telling the shell where everything is. In terminal, the path variable tells it where to look for programs. So when you activate your Anaconda environment, Python will automatically get put, or the entire Anaconda distribution will get put on your path. So then Python can be found automatically. Alternatively, you can also add RMG to your path. So you can export path equals whatever your path to RMG Py is. And then you can shorten this command and just run rmg.py, because that's also an executable file. And then when you're running RMG, output files will always be placed in the same directory, as your input file by default. And a quick note about Anaconda. So if you installed Anaconda this week or relatively recently, then you'll be sort of using the new style for activating environments. And your terminal prompt will have this space at the front, and you should use conda activate RMG env. If you installed conda a while ago, you might not have that base tag at the beginning, and then you'll be using source activate RMG env. The annoying thing is that if you're using one of the approaches, the other command will not work for you. So that's sort of the difference between the two and why you might be needing to use one or the other. So just be careful of that. If you don't have base in front of your username and source activate RMG also doesn't work, then you probably don't have conda set up properly. And then we can also talk about that offline if that's not working for you. Yeah, but in general, I think everyone here is probably going to be using conda activate. Right, and then specifically for RMG, there are some optional arguments aside from your input file, which you can provide. So to see a full list of these optional arguments, you can use the -h optional argument. So if you do Python RMG Py, so here I've shortened it. You need to provide either the full path to RMG Py unless you're already in the RMG Py directory. So just the path thing still applies here. But if you provide the -h argument, it will give you a full list of all the arguments that RMG accepts. Yes?
Now that RMG's in Python 3, do we need to say Python 3 RMG, or does being inside that conda environment take care of that?
Right, that's a good question. I guess the question was whether or not we need to manually specify Python 3. So if you're in your conda environment, the Python command will actually be linked to Python 3. So you can either do Python or Python 3, or you can even do Python 3.7. So any of those will be equivalent in this case. Yeah, but generally speaking, if you're not inside the environment, then what just the pure Python command links to may differ depending on your computer. Right. And then, for example, you can also specify the maximum runtime for your job using the T flag, and then you can specify a length of time. So you have days, hours, minutes, seconds, and then RMG will try to gracefully end your job before hitting that time. And then you can also run in parallel. So right now this only affects reaction generation and QMTP, which I'll talk about a bit more later. But to request that, you can add the -n argument and then specify how many processors you want to use. Yeah, and of course this isn't all the arguments. You can take a look at -H to see everything else that's available. But I think these might be what typically you might need to provide. All right, so then from now I'll start talking about the input files to RMG. So I'd like to first say there's documentation. If you go to the RMG website and the documentation, RMG users, and then there's a full section on input. There's fairly comprehensive descriptions of most of the options. And so in today's presentation, I'm going to go over some of the most like basic options which you'll most likely need to use. There are some advanced options which you can look up on the documentation, and I think there's also going to be a session on Friday where Matt's going to go over some of the more advanced options. And then there's also an examples folder in RMGPy example/RMG with a ton of input files for various cases, which you can always take a look at for examples of various ways to specify the input. Okay, so now getting to the actual input file. So the RMG input file is actually a Python syntax file, which is something that we're looking to change, but as of now, it's still this way. So as you can see, so this is the database block, and I guess this applies for all of the sections which we'll be talking about, but it's basically a Python function call. So you have the name of the block, which is database in this case, and then parentheses, and then a bunch of keyword arguments for specifying the various options. So this is, I guess, the syntax for all of the blocks. So now for the database block in particular, this is probably the most important block, or one of the most important blocks in your input file. This tells RMG which libraries and families to use and generating your model. So I guess Matt just now talked about like various data sources in RMG, including thermal libraries, kinetics libraries, and then families and group additivity. So this lets you specify which of those you want, except for group additivity, which is always there by default. So you can specify which thermal libraries you want, which reaction libraries. C mechanisms is actually the same thing, or the libraries themselves are the same as the reaction libraries. The difference between a reaction library and a C mechanism is that if you specify reaction libraries, it gets added to the edge of the model. So you can think of it as being reactions that we want to consider, or might want to consider in generating the model. Whereas C mechanisms, if you put a library there, it will go into the core of the model. So this is something that you definitely want in your model, and so the full library will be included as is. Kinetics depositories refers to the training depositories that we use for the kinetics families. Generally, you don't need to change this and just leave it as default. Kinetics families is, so we have 77 plus or minus like a few kinetics families in RMG. In general, not all of the families are going to apply to your system. So default is a list of maybe 40 to 50 families that are generally applicable to most systems. But so default is always a good choice to start with. If you have better ideas of what chemistry you're expecting, you can adjust this. So you can use a list and specify the reaction families that you want. And also add things that are outside of the default list. And then kinetics estimator. So Matt mentioned that we have sort of two main methods to estimate kinetics. One is rate rules, another is group additivity. Group additivity is less accurate, so you'll always just want to leave this as rate rules. Are there any questions about this block? Okay. So then the next part, we've told RMG what data sources we want. Then we need to tell it what our species that we're interested in are. So you need a single species block for each species you want in your model, and there are various ways you can provide this species structure. So you can use NG strings, smile strings, and also RMG adjacency lists. There is this reactive flag, which tells RMG whether or not to generate reactions for the species. It defaults to true, so like in this middle block, RMG will react this oxygen. You'll generally want to set reactive to false for any inerts in your species or bath gases, which you don't want to be generating reactions for. Of course, like if you are generating a mechanism for nitrogen chemistry, nitrogen will probably not be inert in that case.
Here, like, do we need to give like transportation parameters if we don't provide smiles structure?
So for RMG input files, you can't provide transport parameters at all. So you can only provide the structure, which RMG needs to be able to generate reactions for these species. So in an RMG job, RMG will estimate transport properties for all of your species.
Okay, if we give smile structure, then automatically it takes from library, right? It's transportation parameter.
It will take transport properties from libraries if the species is in a library. But for species which aren't in transport libraries, we will estimate it using, I don't remember the exact method, but some sort of group additivity approach to estimate transport properties. Any other questions? Okay, so we have the data, we have what species we want, and now we need to specify sort of the reaction conditions, which you do so by specifying a reactor. So in general, you must specify at least one reactor in your input file. Otherwise, we don't know what conditions to simulate the mechanism at. So there are a couple of different types of reactors. So first, we'll start off with the simple reactor. So this is a homogeneous constant TP batch reactor. So you need to specify the temperature, pressure, your initial mole fractions. And here, these are the labels that you gave to your species in the species blocks. So I didn't note this, but yeah, so you have labels for each of your species, and these will be used to identify your species in the following blocks. So here we have N2, O2, and ethane. So these top three are required, and they specify the conditions of your reactor. And in addition to that, you must specify at least one termination criteria. So termination criteria is something to tell it when to stop this reactor simulation. This is unrelated to your overall RMG simulation. This is only referring to each reactor simulation that we do, which is done potentially multiple times per iteration. So there are various ways you can specify this. For example, termination conversion means that you can specify some species, and when say 99% of that species is gone, then we will stop this reactor simulation and then move on to the next step of the RMG job. You can also specify termination time, which is very straightforward, and termination rate ratio, which is slightly more difficult conceptually, but it refers to sort of the rate relative to the characteristic rate of, the characteristic rate at any time relative to the maximum characteristic rate of the simulation. So for example, when you have a lot of things reacting, your characteristic rate will be very high. And then, so over the course of the simulation, it will go up as things are reacting, and then it will go back down once most reactions are done. And then so this sort of gives you, compares that maximum value to your current value, so that once you can think of it as sort of reactivity drops to below some threshold relative to the maximum reactivity, then you'll stop the simulation. I will talk about these termination criteria a bit more in a moment. So in addition to specifying a single temperature, pressure, and mole fraction, you can also specify ranges. So this is something that has made building RMG models a bit simpler. So before, I guess first, for specifying reactors, what you generally want to do is specify conditions that are relevant for whatever system you want to model. And in most cases, these systems are not necessarily a single temperature. So if you're like modeling a flame, for example, you might be interested in very wide temperature range. Or a lot of experiments will manually adjust the temperature range of their reactors to see how behavior changes with temperature. So then you want a mechanism which is valid over all of those temperatures. So before, with just these like single temperature pressure conditions, the recommended approach would be to specify multiple reactors. So you can have as many reactor blocks as you want, and then you can put different temperatures in them. And RMG will build a single model which is valid at all of those conditions. Now, the recommended way to approach this is to actually put a temperature range within a single reactor block. And then RMG will use a pretty fancy algorithm to sort of randomly pick points within this range to simulate at, but in a way where it will explore the full range sort of in a so there's some optimization involved to explore the full range in an optimal way. But then the idea is you only need to specify one reactor, but RMG will still look at or try to simulate the full range or of all of your ranges. So like you'll have a 3D potentially space of parameters, and then it will jump across and simulate at various points within that space. Yeah, so it's an easier way to specify ranges. One thing to note is that, or two things, if you're specifying a range of mole fractions, so for example, if we want to see, have this mechanism be applicable for ethane mole fractions from 0.05 to 0.15, you need to specify balance species to basically balance out when RMG changes the mole fraction of ethane. So like if we increase ethane, then the concentration of something has to go down. So this tells RMG which species to reduce. And then the other thing is this NSIMS parameter. So one issue with using this sort of range reactor is that each time you simulate it at a different condition. So it's possible that at one condition, the chemistry might be complete. So you might, RMG has identified all the important pathways already, whereas at a different condition, there might still be stuff that needs to be explored. So NSIMS is sort of a way to make sure that you explore everything at all the conditions. So technically, it's the number of simulations at these different conditions which must finish without identifying any new chemistry before your overall RMG simulation finishes. So if we specify 10, for example, that means there has to be 10 simulations, all at different conditions, where we don't find any new chemistry, and then once that happens, we'll say, okay, we're pretty sure that we've covered the space, and we can stop the RMG simulation. So I think Matt's recommendation for this value is somewhere around 10, plus or minus 2 maybe. So of course, the higher this number is, the stricter the requirement for completing the RMG simulation is, so the longer your run might be. But then also the more sure you are that you've covered all the important chemistry. Yeah?
What is the output from something like this? Is it going to give you reactors that are important at condition 1, condition 2, or is it trying to give you something that's applicable for everything?
Right. Yeah, so the question is what's the output from something like this, and whether or not you'll get different mechanisms for like different conditions. And the answer is from any RMG job, regardless of how you specify the input, you will get a single mechanism. And for range reactors, or if you use the old approach of specifying a ton of single reactors, what RMG will do is, so RMG will sort of keep the same core and edge for all of the reactors. So then all the reactors will sort of be feeding in chemistry to the same mechanism. So then at the very end, you get one single mechanism which is applicable at all of the conditions. Does that answer your question?
If you guys have to choose out of
so
Thinking it might be more keep them as separate ones, but I don't know for sure.
yeah, so I guess this is sort of a very general, maybe philosophical question. So technically, there's one set of chemistry, right, that governs everything. With chemical mechanisms, because we can't capture all the chemistry, we try to just capture the stuff that's important at a given condition. And then if you have multiple conditions, the chemistry might vary, but in theory, it's always possible to just combine all the chemistry together and then have a single mechanism. So like, all our rates are temperature dependent, right? So you're going to have the same reaction at all of these temperatures, but its rate will vary, and then its importance might vary. But if it's important at any of these conditions and you include it, then basically for that particular reaction, then you're set. Right? Yeah. So if you do specify a very huge temperature range, then your mechanism will be guaranteed to be larger than if you just specified a single temperature. Okay. I forgot to mention, I guess a simple reactor is also gas phase, in addition to being a homogeneous batch reactor. We also support liquid phase reactions to a certain extent. So you can request a liquid reactor, which is then of course liquid phase. Still constant temperature, pressure really isn't as applicable with liquid reactors. You specify initial concentrations instead of initial mole fractions. And so you also need to specify at least one termination criteria. And with liquid reactors, you get this additional option of specifying a constant species. So in some systems, you might have a species which is in excess and more or less at a constant concentration throughout the entire reaction. So this lets you specify that. And the other requirement for using a liquid reactor is specifying a solvent. So you do that with this separate block called solvation. And it takes a string referring to the label of a solvent. And it has to be an RMG supported solvent. So I think there's a list of maybe a dozen or 2 dozen solvents that are supported in RMG. The key requirement being that we must have solvation corrections. Right? And there's a list on the RMG website. If you go to the database, solvation, libraries, solvent, there's a full list of all the solvents that are supported. And then if you find a label, you can specify that here. So other than that, liquid reactors sort of function the same as simple reactors. You can also specify temperature ranges and concentration ranges, or you can specify multiple liquid reactors. All right, so then talking a little bit more about termination criteria. So a common question might be, how do you set these termination criteria? So again, remember that these termination criteria refer to a single reactor simulation for your mechanism. So for termination time, this is generally the most straightforward thing to set. If you know how long your reaction takes, or if you're comparing to an experiment, you know how long they ran the reaction, then this is a very easy thing to set. So if you're comparing to experimental data, you can just set it to be the end time of the experiment. But this can be difficult if you're sort of trying to predict the reactivity for just a random chemistry, and you're not necessarily comparing to experiment, because you might not know exactly how long most of the important reactions take to complete. So yes, I guess that's just one thing you need to keep in mind when you're setting this. You don't want to set it too early because you might miss a lot of important reactions. If you set it too late, then the important reactions will have happened already, and you might start adding in random things that aren't important to your system, because at that point the characteristic rate might have dropped so low that then you're just sort of adding in random reactions and species. Termination conversion is like the conversion of any species in your, or any initial species in your reactor conditions. So for this, you might also have some general idea of what you want. So if you want, say, 90% conversion or 99% conversion of your initial reactant. But one difficulty is that early on in the RMG simulation, when your mechanism is still very incomplete, it's very possible that you're not going to hit this termination conversion at all because you don't have enough reactions to actually react your initial species. So if you were to only set termination conversion and you don't have enough reactions to react your species, then the reaction or the reactor simulation will just continue on forever because you're never going to consume your initial reactant. So if you're setting termination conversion, it's certainly a good idea to also set a termination time, even if the termination time is maybe a slight overestimate, so that you're guaranteed to not be constantly simulating your reactor. Right, and then the third option is this termination rate ratio. So as I sort of explained earlier, it's when the characteristic rate at any time reaches some fraction of the maximum characteristic rate. So in systems where you actually do have sort of a case where the characteristic rate, or which roughly corresponds to the amount of reactions that are happening, goes up and then goes down, this can be a very good criteria because then you're pretty much guaranteed to have passed the important chemistry. But if you have systems where there might be, for example, two stages of chemistry, then this might be dangerous because you could miss the second stage. So I think this is not super well tested, but you can always give it a try if you're interested. Are there any questions? Okay. So I guess before, that was all defining sort of the system that you're looking at, your data sources, your reactors. Now, from this point on, it's sort of parameters to help RMG generate your model. You can think of them as hyperparameters if you're into machine learning. First, there's this model block, which is maybe the bulk of these parameters is in here. So there are a lot of tolerances in RMG. So there's first, probably most importantly, is this tolerance move to core. This is the main criteria for selecting new species. So if you have a smaller value, you're going to end up with larger models. There's another tolerance called keep an edge, which is a criteria for flux pruning. So what pruning is a way to sort of remove species which you think might not be important to keep your overall edge size small and more manageable in terms of memory use. So this is also if you have a smaller value, you'll have a larger edge size. And tolerance interrupt simulation is related to when we stop the reactor simulation. I'll explain these more on the next slide. And filter reactions is an option that basically we think you should always have on. So it's primarily a speed up mechanism, but the idea is that we'll only generate reactions between any two species after the concentrations get to a certain point. And this is calculated based on sort of the collision limit and whether or not the concentrations are enough to react of these two species. In reality, would be enough to react together. Yeah. So this greatly reduces the how many times you generate reactions because we'll only do it for species that actually get to sufficient concentration. And there's currently ongoing work to make this even better by specifying different thresholds for different families because the maximum rate of reaction for a different reaction type might be different. So basically if we can so right now we have a very conservative threshold. So if you can reduce that or increase, I don't know, if you can make it tighter, then you can even further reduce how many times you react species.
Sorry, I have a question about this threshold. So will it filter all the reactions that's lower than that threshold or higher than that? So we're talking about collision rates, does it mean that everything higher than that is non-physical? Is that a thing that we're trying to tell the model?
Not entirely. So this, I guess this doesn't inherently filter by reaction rate. So basically, I think we have two species concentrations. We have some estimate of the collision limit. Or I think it might have to do with how fast they could potentially diffuse and hit each other, and then we compare that to the collision limit. And then if it's, wait, that doesn't make sense. Sorry. Yeah, I don't remember the exact math, but for any two species, if we think they're not going to run into each other and react in a given amount of time, then yeah, I guess I could help.
So there are different thresholds. There's one for unimolecular reactions and one for bimolecular reactions. For unimolecular reactions right now, we have the threshold of Boltzmann constant times the temperature divided by the Planck constant times the concentration of the species that we're including. And if that rate is larger than the characteristic rate times the tolerance, then we will cut off that species. And the similar approach is used for bimolecular reactions, but the threshold is based on the collision of two H atoms at 1,000 Kelvin, and we are including the concentration of each of those. And if that is larger than the characteristic rate, then we are not considering.
And do you have an idea of how many percent of the reactions you actually filter with this?
No, we haven't done the comparison because right now the user can also adjust the threshold. So depending on your use case, you can increase or can increase or we can turn it to gold and set it up for time purposes.
Yeah, so I think in tests, so I guess, as I mentioned, the current thresholds are fairly conservative. So in all the test cases, we never filtered out any important reactions. I don't know exactly what percentage of reactions do get filtered, but I guess, so filter might not be a great word in the sense that it's not done after we generate the reactions. Right? So we sort of try to predict whether or not two species are important enough to react together. And it's always possible later on in the simulation that they'll reach sufficient concentrations to then react.
Do you
Yeah.
account for the fact that a reaction might be very slow versus the one reaction might be very fast versus the
We don't, but I think even very slow reactions will be above this, like will pass through this tolerance. So this is more of a physical, like it should be impossible for any two reactants or one reactant to react at this rate. Does that make sense?
Can we just review, I forgot about this one, when we say tolerance with 0.1, where's that 0.1 mean?
Right. So it's relative to the characteristic rate, which is I think like a root mean square average over all of the rates at that time, or all the reaction fluxes at that time. Right. So then, if the flux of a given reaction is past this tolerance, so the flux of the reaction relative to the characteristic rate is greater than this tolerance, we'll add it. So I have a diagram on the next slide, which sort of shows exactly what these tolerances mean. Right, so filter reactions, and then there's the simulator block, which lets you specify solver tolerances. So you have to specify an ATOL and an RTOL. Sensitivity tolerances are optional. These are the default values. And I think Matt mentioned that at least for ATOL, you don't want it to be any larger than 1e-16. You can make it smaller if you're having trouble simulating your system. Right. So then, what these tolerances actually mean? So this is sort of a plot of fluxes to your edge species. So like A, B, and C might be different reactions as a function of your reactant conversion. So if, for example, you specified a termination conversion of 0.9 something, what RMG would do is simulate your reactor until it hits this conversion, right? And then along the way, it will check at each time step the fluxes to all these edge species, or fluxes to edge species, or in other words, through an edge reaction, and compare them to these tolerances. So, as I mentioned, the main tolerance is this move the core tolerance, which is the threshold for adding a species to the core. So, say we're simulating, and then the species A passes this tolerance, then we will identify species A as being something that we're going to add into the core as soon as we finish this reactor simulation. And then let's ignore tolerance and nerf simulation and keep an edge for now. So then if, for example, you didn't set those, or we're not caring about those, we will continue simulation until we end at the termination conversion. And then because we identified A as passing the tolerance, we will add A into the core and continue to the next steps, like reaction generation. And then on the next iteration, we'll, I guess, simulate again. If you have this tolerance interrupt simulation, then the moment any flux passes that tolerance, we'll stop the simulation. So in this case, if we hit the flux to species B passes that tolerance, we will end the simulation here instead of going all the way to the termination conversion. And the main reason why you might want that is just to save a bit of time and not simulate the rest of the system. Tolerance keeping edge is related to pruning, as I mentioned. So in this case, if species C is under the tolerance keeping edge the entire time of the entire course of the simulation, then it will be sort of put up on the list of species to be pruned. Because its concentration is so low, we don't think it's necessary to keep around. The important thing to note about I guess tolerance keeping edge and pruning is that it will only happen if you actually reach the termination criteria that you set. So in that sense, this tolerance interrupt simulation might be something that you want to be careful about if you want to do pruning, because if we, for example, hit this interrupt simulation and we don't simulate all the way to the termination conversion, then we won't actually prune. So generally, you want to set the tolerance interrupt simulation higher if you want pruning, so that if nothing passes it, we will get all the way to the termination conversion. Does that make sense? Any questions?
So interrupt simulation means that it will like go back to start over and try to install it again, like something like
No, so it will end the current simulation.
yeah.
And if you have already identified a species that passes the tolerance move the core, it will move on and add that species to core, generate reactions, and then so on and so forth. I don't know what would actually happen if that tolerance interrupt simulation was lower than your tolerance move the core, which you should never do. But because in that case, you might end the simulation before identifying anything to move to the core. I don't know how RMG would react to that, so don't do that. If you're not doing pruning, the general recommendation is then to set tolerance interrupt simulation to be the same as tolerance move the core. Because then, as soon as you identify a species to add, you can quit early and actually add it.
I was going to ask why would you finish and iterate the whole thing and then how you had to start over.
Yeah. main reason would be if you want to prune. Another reason related to sort of a slightly more advanced feature that I didn't mention is that you can now actually add more than one species per iteration. So in this case, both A and B pass this tolerance move to core. So if you had set, it's called num species per iter, I think, to 2 or more, then we would add both A and B to the core on the next iteration. In that case, you might not want to set tolerance and error change simulation to be the same, because otherwise you would only ever get the first thing.
Once the species get into the core, that species will not go back. There's no chance for those species to go back to the edge. It will always stay on the
Yeah, so it's unidirectional. We will only ever move things from the edge into the core, not from the core back to the edge.
Is there any reason why you might set the number type or instead of 2, what if you set it to 1 or if you just set it to 5?
So right, so the question is about setting the number or number of objects per iteration higher or lower. So the default is 1 because that was sort of maybe historical. That was how it used to be done. And then we decided that it didn't seem to make that much sense, or like why you wouldn't necessarily have to limit yourself to 1. But sort of a consideration for why you might not want to have it be too high is on a given iteration, your chemistry is incomplete. So sort of what we think of is the first thing that passes this threshold. If you add it to your core, then your chemistry might change. So then the important species might be different on the next iteration. So if you go through one simulation and say add all of the species that pass this tolerance, maybe if you had just added the first one, the chemistry would have been different to the point where the rest of the species were not actually important. So I think that was sort of the motivation for not having it to be too big. But if you do have it higher, then your model does grow faster. So it can help with just building models faster.
Am I correct that so from your core, you have your reaction to your edge, and then you don't have any further reactions?
Yes.
Would it be beneficial to add further reactions, like one or two steps? Because you have more chemistry and you have better fluxes, so it might be better reasoning to add more.
Right. So the question is about whether or not we should add additional steps from edge species to further or farther products. And so I don't really know how that will work within our current framework, because we only simulate the core, and then we evaluate the edge by we evaluate these edge fluxes by taking core concentrations multiplied by the edge reaction rate. So we don't know the concentrations of the edge species. So then, at least sort of practically, we can't really evaluate the flux to a second layer of edge species. But and then thinking about it in a different way, when we add edge species to the core, then we are sort of extending in that direction and then evaluating the next layer in that particular direction. So it may be sort of a balance. I mean, that's something we are sort of already doing, but yeah. But I think in general, it could be true that, of course, looking farther would give you a better idea of the chemistry, but I think there are practical limits to how to accomplish that. Any other questions? Okay, so there's also this options block, which has miscellaneous options regarding the RMG job. So, yeah, sorry, this is explanation of 5 of them here. So generate seed each iteration. So you can have RMG automatically save a seed mechanism, which can then be used to restart the job if it fails, or you can use it in a completely different simulation just as a seed mechanism if you want. By default, I think this is true. If you set it to false, we will only generate it once your model is converged. Save simulation profile saves the concentration profiles for each of your reactor simulations. And you will get 1 profile per iteration, I think. Save output HTML generates the sort of pretty HTML of the KimKim file on each iteration. This can be very expensive for large models, so we generally recommend you turn this off during during model generation, because you can always generate it from the KimKim file after the fact, and it's the exact same output. So generally there's no need to keep this on to have it do it every iteration. Same thing for edge species, or similar thing for edge species, in that it can be expensive if you're running a large model. Unless you're explicitly interested in what's being formed in the edge, then you generally don't need to save them, because the core is the actual mechanism that you want. And then verbose comments is an option to basically save full comments for how we average the tree for kinetic simulation. I would say keep this off. You generally don't need it because you're going to end up with pages on pages of comments because of how sparse our trees are. So then when you average them, it's an average of a ton of things. Okay, so now these are sort of the extra features that can affect your model generation. So one is feature is pressure dependence. So I guess pressure dependence is, so we typically have temperature dependent rate coefficients. You can also have them be pressure dependent if you have a reaction network and wall skipping reactions. It's generally important for small molecules, high temperatures and low pressures. High and low are in quotes because it's somewhat relative depending on the size of your molecule and exactly the reactions that you're looking at. So I guess the key sort of arguments in this pressure dependence block is the method that you use to calculate the phenomenological rates for these reactions. So there are 3 supported methods: modified strong collision, chemically significant eigenvalues, and reservoir state. So modified strong collision makes a ton of approximations, but it's the most robust method, which is why it's the default method for RMG simulations, because you're less likely to run into errors where it fails to calculate the rates. Chemically significant eigenvalues is the most accurate, I think, but the downside is that it often will fail. And then interpolation refers to how you're actually going to fit rate parameters to the calculated rates. So basically you're going to have a rate constant that's a function of temperature and pressure. So we recommend using Chebyshev. So this is a type of polynomial to fit to this to the TP dependent rate. The 6 and 4 refers to how many parameters you have in the temperature dimension and the pressure dimension. Alternatively, you can use Plog, which is basically a set of Arrhenius rates at each pressure. Chebyshev tends to give better fits. So. And there will be more, another session explicitly on what pressure dependence is and why it matters tomorrow. Yeah.
What's the additional computational time?
I don't have a specific number, but yes. So your computational time will definitely go up if you activate pressure dependence. I have seen that my model seems to grow faster when pressure dependence is on, but that could be for completely different reasons because you're considering a lot of different pathways. But yes, pressure dependence is computationally somewhat expensive, but it's not super expensive. So if pressure dependence is important for your system, we'll generally recommend you turn it on. It's not expensive to the point where it's not worth running.
And will it do pressure dependence for all reactions?
Oh, right. Good question. So you can set the maximum atoms for the size of the molecule that you want to consider pressure dependent for. So as I mentioned, it's generally important for small molecules. So setting this somewhere around, I think, 15, 16 will limit molecules that are smaller than that to go into pressure dependent networks.
And not for bimolecular reactions? Or also for
So you have bimolecular entrance channels. So it's usually like some addition reaction, and then that goes into a network.
yeah.
But for the
Or
I guess-
hydrogen abstraction reactions? Also
oh yeah, no, hydrogen abstractions will never be pressure dependent.
Yeah.
I don't know if you can have a wall skipping thing that ends up being a hydrogen abstraction, but
Well, I mean, it's connected by unimolecular reactions. You can have an output channel, but the output is
Well, like,
output is
could
connected
you
to
have-
a unimolecular isomer.
oh yeah, you can never have an
You can
addition
never
and
have
then isomerization.
Yeah, I think
yeah. So hydrogen abstraction, I think, will
But
always.
you have like an internal system of deciding which reactions to apply it for and which you don't have to apply it for?
So I think the criteria is just if either the reactant or the products is unimolecular, it will get added to a network, or we'll try to add it to a network.
Yeah, I think time is about it's similar order to the order of the RMG runtime. So you maybe see like 50% runtime increase, 100% runtime increase, those kinds of numbers at least. I think.
Yeah, but again, it's sort of hard to measure because your model is completely different.
And so you can only limit it by adding the maximum atoms? There's no way to like say, okay, do it for aromatics, but not for regular species? Or?
Yeah, so right now this is the only option you have for limiting what species are considered.
So this is for RMG simulations, right?
Yes, this is for RMG simulations.
Okay. So then the question is, where the numbers come from? Because you have a kinetic library and the thermal library.
Yes.
Yeah, where the actual numbers come from?
That's a very good question. So RMG uses, so there's like a group activity approach for estimating frequencies for any given molecule.
Okay.
So RMG has I think it's sort of like a group activity type scheme for estimating frequencies for any arbitrary molecule. So it can estimate the frequencies. It has the high pressure limit rates, and it will use inverse Laplace transform, I think, to convert them to K of E's.
So when you make groups, like group validity, like groups directly, do you need to put like another information to make this frequency things?
So the frequencies is a completely separate tree or database, if you will. It's not related to thermal group activity. So it's like there's a StatMech database, which has these trees, and the trees don't have any thermal values. They just have, I think, frequencies associated with certain groups.
Or they have essentially they have ranges of frequencies, and then it figures out how many frequencies they're supposed to be, and then it samples within that range of frequencies. It's and then there's also a system through which it decides it deals with rotors and lumps rotors together based on how much information it has and how many parameters it's trying to determine from how much information. Because there's a little bit of an information asymmetry in the problem.
It's a different way. Currently, it's a very complicated way of estimating the density states, which works if you don't have any information. If you did have pumped energy calculations, then you can do it a lot better way. But that means someone would have to build a database to keep track of that information, which so far we don't.
Also, I realized that the pressure dependence calculation in RMG, they're just not using arcane, it's just estimating.
Yes, so the core pressure dependence calculation code is the same. The main difference between RMG estimates and arcane calculations is where the StatMech information is coming from. So with arcane, you're going to run a quantum chemistry job, and you'll know the exact StatMech information. With RMG, we do this estimation script. But you might notice this pressure dependence block looks the same as the one you would provide in arcane.
This might not be related, but then how RMG calculate our TST rate?
So the TST rate is from the normal estimation method
So
from kinetics families.
Yeah, okay. Yeah, if you have to get free energy, then you can calculate the TST. So instead the
Well, so we estimated from the kinetics families, right? So we have rate rules, and that gives us the high pressure limit TST rate. Does that answer your question?
Do you have a database which you check limits or fields or?
So some of the libraries, kinetics libraries, will have these pressure-dependent rates, which people have calculated, but we don't have a dedicated database for these.
For low pressure dependence, Arcane is better, or this RMG is better?
Right, so I mentioned like the core calculation code is the same. So Arcane is definitely better because you'll be using quantum chemistry calculations. So then you'll have the actual data for your species, and you'll get much more accurate rate calculations.
How accurate in the low pressure region?
Oh, how accurate in low pressure?
Depends on
I'm not sure if there's a general answer for that. Yeah, I think so. When you're running RMG jobs, using pressure dependence will definitely give you much better results than not using it. I don't know exactly how that compares to if you were to calculate the full mechanism or the full surface using Arcane, which you could consider as sort of the true value to an extent, depending on level of theory, of course. Yeah, so I think I'm running out of time. But, are there any other questions on pressure dependence? Okay, so there's still a couple more blocks to go through. So you can also specify species constraints for your model. So this is generally recommended that you do to sort of limit the search space for what RMG needs to look at. So importantly, you should always set this allowed parameter in case your input species or libraries have species that will fail these constraints. If you don't have that allowed block, RMG will raise an error when it encounters something from a library. So generally, we recommend setting maximum radical electrons. So maximum 2 radicals is sufficient for most systems. In some cases, you might want to set it to 3 radicals for nitrogen, like you're simulating nitrogen chemistry, for example. And in our experience, if you're doing very large pyrolysis models, where setting 2 radicals is making RMG take a very, very long time to run, you can sometimes set it to 1 and get a decent model. But this is sort of, you might miss some reactions. So this is sort of an approximation, and should be careful with that. And then element-specific limits, you should consider based on the types of chemistry you're expecting. So for example, if you're doing pyrolysis where you're only interested in how the molecule breaks down, you might want to set it to be a few atoms larger than your initial reactant size, so you don't start getting like pH formation or polymerization in your reactant.
Can I comment on that? But be careful, you have to allow for some reaction that will kill your radicals. And so often, through the lower temperatures, the starting radical you have might survive, and you have to have it recombined. And so then you might have to go through twice the size of your original.
Yeah.
If you don't do it, you get quite strange results. But high enough temperature, the radical, the initial one will fall apart to some small stuff, and you don't have to do it.
So another option you can use related to thermal estimation is the QMTP module, which stands for Quantum Mechanical Thermal Properties, I think. So this does on-the-fly quantum calculations, but using very low-level semi-empirical methods. And we support MOPAC and Gaussian. So compared to group additivity, this is extremely slow. So, on an absolute scale, it's still reasonable. Maybe much less than a minute per species, right? So, in general, we don't necessarily recommend using this now because group additivity accuracy has improved a lot. So QMTP was originally intended for cyclic species where we couldn't get the ring strain correct, but we have since added a lot of polycyclic heuristics to group additivity to improve our ring strain estimation. So in most cases, QMTP is probably not worth the cost of running it. But you can do in parallel now, which does help on that front. And then another thermochemistry estimation method is using the machine learning thermo estimator, which is a neural network estimator using graphic convolution, which Matt mentioned earlier, trained on quantum calculations. In some cases, it can be better than group additivity, but one thing that I found is it's sort of hit and miss. So it's not like consistently better or consistently worse, which would be bad. But like for certain species, it's better. And to sort of help make that useful is you have a ton of options for limiting the types of molecules that you estimate. So then you can try to sort of have this be the estimator for the set of molecules that it's better than group additivity for. And in general, you should, it's better for very weird cyclic molecules. So you can set only cyclics to true, and then min cycle overlap is related to how fused the cycle is. So 0 means, I think, you just have cyclics, or independent cycles. 1 is a spiral cyclic molecule, 2 is a fused cyclic, etc. Right, so if you're using machine learning estimator, I would recommend not setting the options. If that makes sense. And then, okay, this is the last thing, is RMG now has functionality for modeling heterogeneous catalysis via the surface reactor. So this is relatively new. We merged the RMG cat fork earlier this year. So I'm not super familiar with this, but you need to set some catalyst properties and then define a surface reactor block as opposed to simple or liquid reactor. So this is primarily developed by Professor Goldsmith and Professor West. So if you want to work with this, they might be good people to ask. I don't know how much time I can go over. Do you know what the next session is? Okay, so what do you think? I have maybe 5 more slides.
This stuff's pretty important though. I feel like this.
Okay.
I feel like this section is pretty important.
Right. So this section is about how to pick your libraries into mechanisms in the database block. And so this is very important because you want to have good data which is relevant to the system that you're simulating. And depending on which libraries you pick, you can get very different final models. Yeah, and I guess key point that you always want to be careful with is to not provide libraries or just parameters in general that are fitted, because fitted parameters will work very well for the system that they're fitted for, but if you're applying to a different mechanism, then it might completely mess up your mechanism. So if you're working on modeling oxidation or combustion of oxygenated species, so I guess I won't read all of the thermal libraries here. This presentation will be available later for you to reference, but there are some very good thermal libraries with data from ATCT or high-level calculations, which are good for oxygenated compounds. FFCM is somewhat popular mechanism for C0 to C2 species, but do note if you use FFCM for kinetics, you should always include. You should also include FFCM thermal library because they're sort of FFCM is somewhat optimized within uncertainty bounds, I think. So you want to make sure that pairing is matched up. If you're working with nitrogen compounds, there are some thermal libraries that alone has compiled primary NS nitrogen current and this calculated library, and also kinetics libraries. Similarly with sulfur, so for kinetics libraries for sulfur, there's a lot of small libraries that were generated for a specific sulfur species, and those are all located in the sulfur folder. Depending on what specific molecule you're modeling, some of those libraries might be helpful.
So like we saw sulfur for nitrogen, we're saying like different options for these different libraries versus kind of differences between them, like why they're not all lumped together, like which one easy or
Yeah, so in general, has to do with the sources of the data. So something that we really wanted to do is compile like our recommended libraries with sort of data from all over, but we've never really gone to that. So most of these libraries are either, so like they might be from a specific paper or a specific mechanism from literature, or calculated by one person from our group. So like thermo DFT, CCSD, etc. Is from a set of calculations that someone from our group did, I think. Sulfur library is also a set of, it might also include literature data, but calculations that someone who was working on sulfur mechanisms in our group compiled. And then primary NS was compiled by someone else. So like, right now there's not really a great structure to these libraries, but they're generally associated with different sources or people. Right, and then if you're working on aromatics chemistry, there's a fairly large library called cyclic aromatics, which we're working on improving with 1D hindered rotors, which will be out soon, hopefully. And then one set of kinetics libraries specifically for getting from first to second aromatic ring formation is in this folder. So this includes a lot of literature data on pathways from first to second aromatics. Yeah, so in general, so you can always come back to this for reference, but if you have questions about what libraries to use, you can always come ask people in the group who are working with those chemistries, and there might be more updated recommendations than what's on the site as well. Yes?
Can you put like a rating of the libraries, like out of 7, something like that, so easily we can find out if I choose between two libraries.
Yeah, I think that's a good idea, and it would be something that is fairly straightforward to put together. So I think we could definitely do that.
Here's my question is related. Could we identify libraries that do need improvement? Because it was mentioned previously that some of the older ones, there's maybe not as many decap comments, and therefore may not add references, etc. Could we identify libraries that do need that improvement?
Yeah,
So
so
similar question, I guess.
I think the general response is that yes, there is a lot of improvements that can be made to our libraries.
But it's a base, so if you need that library, you can work on improvement.
Right, but I think the issue has been just that people don't have time to go through and organize things. But the idea might be to have a hackathon or something to really make everyone go through the libraries and organize them and add references or remove fitted things.
And certainly sometimes people in the research get very heavily involved in a library because it's really crucial to the system they're doing. And so it'd definitely be worthwhile if they would have annotations because they'll know about it.
Yeah.
For somebody coming in cold, their library might be quite hard to learn enough about it to know what's good and what's bad.
If you use, for example, 3 thermal libraries and it has common species, it will take one from the first library?
Yes, that's a very good question. So if you have multiple thermal libraries with common species, we will respect the order that you list them in your input file. So yeah, so the specification is a list, right? So then we will always take thermal from the first library in that list, which has the species. And I guess the same applies for kinetics. If you have multiple libraries with the same reaction, then we'll take the reaction from the first library that has it. might depend on where the value came from, but it seems like in general averaging different sources is probably not a great idea, because especially if you have a calculated rate for something and you average it with who knows what, then you have no guarantee you're going to get better, right? And it's most likely going to get worse. Okay, so then the final topic. So I was originally planning to have you run an RMG job, but since there's no time for that, I'll just go through the output that you would expect from an RMG, from after you run an RMG job, and sort of what everything means. So the main file that RMG outputs is the RMG log, which has all sort of the full simulation and sort of information related to that. It can be useful if you know what you're looking for, but in general, it's a lot of information that might not be very useful. Something you should always check is this collision rate violators log. So now at the end of every job, we will go through all your rates and check if any exceed the collision limit. And so if you, and then we'll log them in this file. So you should take a look to see maybe how far they exceed the collision limit, whether or not it's a reasonable rate, and you might want to maybe replace it if it's like some estimate that doesn't make sense. So a new feature in RMG is restarting from C mechanisms. When you finish an RMG job now, we will generate this restart from C.py, which is actually an RMG info file, but with an additional block so that you will restart from the C mechanism that was just generated. So if you would like to restart, you can directly run this file with Python RMG.py restart from C.py, and it will load in the C mechanism and continue generation from that point. Okay, so then the files that you will most likely need are the mechanism files, which includes all your species and reactions. So right now we output files in 3 formats. So there's a Kantera directory with mechanism files in Kantera format. The main mechanism folder is the KimKim folder, which has all the mechanisms in KimKim format, along with the species dictionary with adjacency lists for all the species. And then there's also an RMS directory with the files in RMS format if you want to simulate it in RMS. And I know at least in Kantera and KimKim, I'm not sure about RMS, there are 2 versions of the file. One is called, for example, kim.imp, the other is kim annotated. So to KimKim or Kantera, these are identical files. The difference is that the annotated version includes RMG comments for how each of the parameters is estimated. So if you're interested in looking to see how a particular rate was estimated, you should look at the annotated file and read the comments to that reaction. The comments are also parsable by RMG if you were to load it back into RMG. And then there are a number of supplementary files depending on what options you specify. If you requested pressure dependence, you'll get a PDF directory with all the network files, which are actually directly runnable in Arcane. There's a solver directory if you requested simulation profiles. We can also generate simulation statistics in the plot directory. And if you did request the HTML files, you'll get output HTML plus a species directory with pictures. Yeah. But in general, what you'll need is all in the mechanism files. And then you'll simulate that in whatever software you prefer. All right. Are there any questions? All right. So that's all I had. I hope this helped with understanding the info file and how to run RMG. If you have any questions, feel free to ask us after.